Hello, everybody. My name is Satoshi Hoshino. I am from Utsunomiya University, Japan. The title of my presentation is Discrete Motion Planner based on Deep Recurrent Neural Network for Mobile Robot Obstacle Avoidance in Dead-End Environments. As you can see in this movie, first off, localization and motion planning are essential capabilities required for autonomous navigation of mobile robots. For localization, the environmental map, as shown in this right bottom movie, is built beforehand. Based on the localization result, the robot then plans the path and motion toward a goal destination. In this work, especially, we focus on the motion planning technique so that the robot moves toward a goal while avoiding collisions with obstacles. In previous works, so-called model-based motion planners, such as dynamic window approach and artificial potential method, and etc., have been proposed. In these motion planners, mathematical models were used, and a sensor data represented by X here is fed as input into the model. The model then converts the sensor input to the motion output Y here, and the output is finally sent to the robot. Usually, the motion outputs are velocity and angular velocity, and these are all continuous values. Here, let me show you a movie of a robot based on our proposed mathematical model, VOO, velocity obstacle for occlusion. We can see that the robot successfully avoided the walking persons and moved toward the destination after that. Mobile robots based on these model-based planners are, however, sometimes exhibit different motions depending directly on sensor inputs. Furthermore, it is required to determine the model parameters suitable to navigation environments. On the other hand, in recent years, motion planners based on a deep learning technique have been proposed. Instead of motion planners based on mathematical models, as you can see here, deep learning techniques or deep neural networks are used in order to approximate a relationship between sensor inputs and motor outputs. This is a so-called an end-to-end or E2E motion planner. So far, many E2E motion planners have been proposed for regression problems. For example, the E2E motion planner proposed by Pfeiffer decided the continuous values of the velocity and the angular velocity of a robot from the range data of a 2D LiDAR and goal direction data as inputs. However, in order for the deep neural networks to decide continuous values as the control outputs, a large amount of training data is required. So such data sets increase in the training cost. On the other hand, we have proposed an E2E discrete motion planner in terms of a classification problem. As you can see in this figure, the motion planner was based on a fully connected deep neural network, FDNN, composed of 4 hidden layers. As the input, the range data scanned by the 2D LiDAR and the direction angle were used. The E2E planner decided discrete motion control commands such as straight, right, and left as the outputs. So the network training was done by comparing the classified motion outputs with the desired outputs instructed by a supervisor. This is a so-called imitation learning approach. For the network training through imitation learning, therefore, we prepared these 3 instruction environments with obstacles. As you can see in this picture, the supervisor instructs the motion through a joystick by watching the front display. In this movie, the robot is now moving on the basis of the instruction. Since the robot is equipped with a 2D LiDAR sensor, the range data is displayed for the supervisor. In the instruction phase, training data sets are registered by the robot. The inputs are the range data and the goal angle. The outputs are the motion commands, which are straight, right, and left, depending on the velocity and the angular velocity. So these commands are used as the supervisory signals for network training. Here, let us show you the movies of the navigation results in these two environments with completely different layouts. As you can see, the robot, based on the proposed E2E Motion Planner, successfully moved toward the goal while avoiding collision with the obstacles. However, as you can see in this movie, once the robot stops, it is impossible to restart navigation toward the goal destination. This problem occurs when the environment is changed due to newly appeared obstacles, and a dead end is formed by these obstacles, as you can see here. To our knowledge, mobile robots based on the previous E2E motion planners are not able to escape from the dead end and continue navigation. In order to escape from the dead end, the robot is required to stop and rotate at the same position. Therefore, further motions such as stop, clockwise rotation, and counterclockwise rotation are instructed by a supervisor, in addition to the straight, right turn, and left turn motions. As for the motion outputs, in addition to the motion commands such as straight, turn left, turn right, additional motion commands which are stop, clockwise rotation, and counterclockwise rotation are defined depending on the velocity and angular velocity, B and omega. Here, let me explain the proposed motion planner. As you can see here in this figure, the output units are composed of the 6 motion commands in total. The range data from D1 to Dn obtained from this 2D LiDAR and direction angle are fed as the sensor inputs to the motion planner. In order for the stopped robot to escape from the dead end and continue navigation, it is required to plan motions other than stop, even for the constant sensor inputs. For this challenging dead-end environment, the sensor inputs corresponding to the time series motions are recurrently used in the motion planner. For this purpose, the last hidden layer is connected to both the output layer and the context layer in this step. The context layer is connected to the first hidden layer in the next step. This network structure enables the robot to take into account the time series motions instructed by the supervisor for the dead end. For network training through imitation learning, these 3 environment with obstacles are used for motion instructions. Moreover, here, a dead end formed by the obstacle is also used for escaping motion instructions. For imitation learning, first off, a supervisor instructs the robot to move toward a goal destination while avoiding obstacles. At the same time, the robot registers the sensor inputs and desired motion outputs instructed by the supervisor. These are used in the training data set D. The supervisor's policy is here assumed to be an optimal. So the robot is instructed to optimally move toward the destination for the sensor input by the supervisor. On the other hand, the policy of the robot in the learning phase is represented as you can see here. where theta indicates network parameters. Therefore, the network parameters are optimized where the following objective function in the running phase. By repeatedly updating the policy, it approaches the optimal. In doing so, the reaching motions become increasingly similar in the ones instructed by the supervisor. Finally, this optimized robot policy is used in the motion planner. In this experiment, a mobile robot equipped with a 2D LiDAR as shown in this picture is used for autonomous navigation. For obstacle avoidance, our previous FDNN, which is fully connected feed-forward deep neural network, and proposed DRNN, deep recurrent neural network, are applied to this robot. As you can see in this movie, for dead-end environment, which was given for motion instruction, the robot based on the proposed DRNN successfully escaped from the dead end. For your information, the robot based on the FDNN failed in escaping from the dead end. We also examined the performance of the motion planners in another environment setting different from a corridor. In this environment, the robot autonomously moves from S toward G. For this purpose, the occupancy grid map for localization and motion planning was built beforehand. In this navigation experiment, however, this kind of L-shaped obstacles, colored by white here, were newly arranged between S and G. So the robot based on normal motion planner is trapped by this dead end around here. As navigation results, let me compare the trajectories of the robot depending on the applied motion planners. This figure shows the occupancy grid map. The robot localizes the position by using MCL, Monte Carlo localization, simultaneously with motion planning. First off, we can see that the robot based on the FDNN moved so as to avoid collisions with the obstacles. So the range data used as the sensor input guaranteed the sufficient obstacle avoidance capability. However, the robot stopped at the dead end around here. After that, since the sensor inputs became constant, this robot continued to stop and failed in escaping from this dead end. On the other hand, although the robot was also stopped at this dead end, the context layer played a role in predicting other motions. So the robot was allowed to rotate it at the same position and moved in a direction opposite to the goal destination around here. Finally, the robot successfully moved toward the goal destination even in the dead-end environment. So let me here show you the movies of the navigating robot based on FDNN left and DRNN right. We can see that the robot based on the proposed motion planner DRNN successfully escaped from the dead end and moved toward the goal destination while avoiding the obstacles. Okay, in conclusions, we propose an E2E Discrete Motion Planner in order for mobile robots to escape from dead ends. In the motion planner, deep recurrent neural network was used in order to take into account a time series motions instructed by a supervisor for the dead end. Through imitation learning, the network parameters of DRNN used in the motion planner were optimized so as to predict the instructed motion outputs for the sensor inputs. In the navigation experiment, we finally showed that the robot based on the proposed motion planner successfully escaped from the dead end and moved toward the goal destination while avoiding the obstacles. Okay, that's it. Thank you for your kind attention.